Okay, let's get started. Today's a review lecture, and I've structured it slightly different than I've done things in the past because it's going to be a combination of you solving things and me solving things. And we're not going to fully go through all of these examples to completion, but we're going to talk about the fundamental concepts and principles in how to approach any problem that you're given so that you can figure out property values, how to solve mass flow rates, how to read the problem statement and figure out exactly what it is you're supposed to be solving for. One problem I noticed on the last homework is that many people were solving for the wrong heat transfer component. So rather than the heat rejected, they were finding the heat absorbed. So be very careful when you read the problem statement that you solve for the right thing, because that's automatically points off. Even if you've done that completely correctly, I can't give you credit for solving for the wrong thing. I was generous on the homework. I won't be as generous on an exam if you solve for the wrong thing. I'll give you kudos and a smiley face for knowing how to solve for that other thing, but it's up to you to read the problem statement and know what you're solving for. So we'll look at some of that today, and again, interpreting the language of the problem statement is very important, because sometimes you start reading it and it seems really big and confusing and just this enormous task. But if you just start underlining things and breaking things down one by one, start figuring out what they're talking about with the states, then it becomes a lot more simplified. So some of these diagrams that we're going to look at today seem very complicated. Some of them are bigger than what we've ever done before, but I think you'll see that it's easy to just break them down into their steady flow components and then solve it just like you do any other problem. Okay, it's just a matter of reading the problem statement and knowing where things are. So our exam's on Thursday. Hopefully you're already studying, preparing for that. And I do have a little extra credit assignment that we'll do next Tuesday. Hopefully you enjoy that. It'll go towards a quiz. So up to 10 quiz points, and I'll talk about that in a minute. So today we're reviewing chapters 10 through 13. And the advantage that you have on this exam, of course everything is cumulative just because of the nature of the class, but the way that these cycle problems have kind of broken down, I'm focusing mainly on the topics that are contained in chapters 10 through 13. So of course you still need to know how to solve for steady flow devices and properties and things like that, but you don't have to know all about the Otto cycle and the diesel cycle and the Brayton cycle and those different cycles, because we have other cycles that we're focusing on for the last 4 chapters. Okay, so the extra credit assignment, I thought that I'd have fun with this, since next Tuesday is Halloween. You can come to class dressed up as something thermodynamic related.
Steve PowerPoint.
Okay, so an example of something that would earn you 0 to 1 point. If you had like a name tag that said, I am Maxwell. Like you're dressed up as Maxwell just because your name tag says that you're dressed up as Maxwell. That's like maybe half a point, right? So 10 points, wow me, surprise me, make it interesting, okay? And you will vote, so the person who has the best costume as voted by their peers will win a special prize in the form of an Amazon e-gift certificate. So, quiz points on the line, Amazon gift certificate on the line, make it fun, make it interesting, and we are still going to have class that day, so it's not like just a big, huge party. It will be fun and interesting, but we will still learn new topics and go over the exam. So come prepared to learn. Don't spend the whole weekend making a costume. Still fail the rest of your classes. So just keep it in the back of your mind. Think of something interesting, unique, or fun, and we'll just enjoy that day. Okay, so we're going to get right into it with these examples because I think we want to spend a lot of time on the fundamentals today. In many cases, when I do an example in class, I'll say, okay, this is this, here's the property values, blah, 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 blah. We're going to talk about how to figure out what state it is, reading the problem statements and figuring out which property values are given, because it's not always explicit when it tells you, some information in the problem. So let's look at the first example that's in your packet. The problem number 1 is a steam power plant. So in the last 4 chapters that we've covered, we've talked about power plants, which are power producing devices or cycles, right? We have also talked about refrigerators and heat pumps, which are power consuming devices. So you don't know which type of problem it will be on the exam until you look at it, right? So first thing you should do when you identify your problem is determine if it's a power consuming device or a power producing device. That's a very good benchmark for when you start solving. Because if it's a heat pump or a refrigerator, the thinking is a little bit backwards in that your QL is coming in and your QH is going out, whereas it's reversed if it's a heat exchange or a heat engine. Okay, so this is a power plant. It's a power producing cycle. So let's just look at it. We've seen these before with the high and the low pressure turbine. And do you remember why we do that? Why do we have that high pressure and low pressure turbine? What's the advantage of this cycle over just having one turbine?
You get more power output.
Okay, more power output. It allows you to go to a higher pressure, which gives you a greater power output. What is another advantage?
Better efficiency.
Yeah, it's better efficiency. So your boiler pressure is able to go to a higher pressure, which increases your efficiency, and it also increases your net work or your net power output. So those are the advantages of having this. And is this reheat or regeneration? Reheat, right? So it's reheating the steam in between the two turbines. And it says that in the problem statement. But looking at it, if it didn't say the words reheat, would you know that that's what it is? Okay, make sure that you understand the difference. Okay, so looking at this, how many states do we need to determine?
6.
Okay, 6. And which of the 6 are easy and straightforward to determine from the problem statement?
1, 3, 5.
Okay, 1, 3, and 5. That's what you said?
6, not 5.
Okay, 5, 6, 3. 3 is easy.
All of 4.
Let's get started, right? Okay, so this problem is interesting because it's a little bit backwards than how we normally receive these problems. Instead of being given the inlet conditions on the turbine, what are we given? Outlet conditions, right? So recognizing that and noticing that you have the outlet conditions and that you have to solve for the inlet conditions is important, right? So you don't accidentally put the wrong things or the right things in the wrong places. So let's just get started. The plant maintains the boiler at 5,000 kilopascals, right? So where is that pressure?
5.
5. Okay.
3.
Yeah, 3. Okay, 5,000 kilopascals is the boiler pressure. So that's what comes into this high pressure turbine. Is it 5,000 kilopascals anywhere else?
As well.
Yeah, state 2 is 5,000 kilopascals. So state 3 and state 2 is 5,000 kilopascals. The reheat section is at 1,200 kilopascals. So what pressures are those?
4 and 5.
Okay, 1,200 and 1,200. And the condenser is at 20 kilopascals. So what state?
6 and 1.
6 and 1. So this is 20 and this is 20. Okay, so we have pressures at every state. Pressures are known at every state. We need a second value at each of those states in order to fix the state. So at state 1, what's the second thing that we know? Okay, so for the Rankine cycle, we always assume that it's coming out as a saturated liquid. So that means our quality is what? 0. Quality is equal to 0, which means that our H is going to be equal to what? H sub F, and V is equal to V sub F, and S is equal to S sub F. Okay, so we can go to the property tables, table A, this is steam, so A5, and look it up. Everything is known. So state 1, check, we know everything. Okay, what about state 2? How would we find all of the properties at state 2? We know the pressure. What's the other thing we know?
Yeah, that's what that's.
Okay, it's isentropic, so state, or the entropy at state 2 is going to be equal to the entropy at state 1. Now, do we have tables that go to down to 5 megapascals? What's the minimum pressure in the compressed liquid table? 5 megapascals. Okay, perfect. So we can use S2 is equal to S1, look it up in the table. So compressed liquid table is A7. Or if we didn't have values in a compressed liquid table, what's an alternate way of doing it, knowing the pressure?
Compressed liquid approximation.
Okay, can we make the compressed liquid approximation when we only know the pressure and not the temperature? Yeah. So when we know the pressure, we know it's an isentropic pump. What other tools do we have to help us find that second state?
We're going with H value?
Yeah, the H value. How do we find H?
Pump work. Plus
Work.
H1.
Okay, so the work of the pump. What's the equation for the work of a pump?
H minus H1.
Okay, work of a pump is H2 minus H1. The work of this pump's not given. What's another way to solve for it?
Specific volume times area.
Yeah, so it's also equal to V1 times P2 minus P1. P2 and P1 are known. V1 is known. You look that up. It's V sub F. So we can solve for H2 is going to be equal to H1 plus V1 times P2 minus P1. Okay, so this is an isentropic pump. What would we do differently if the pump was not isentropic? Would we still do this initial
You still
analysis?
assume that it's isentropic, but then you use the isentropic efficiency equation for the pump to find the H2A, and then you go back and find the next temperature.
The
actual
S2A, right?
S2A.
Okay, so if we have an isentropic efficiency for this pump, and I don't remember the equation exactly off, so it's the work, actual work will be higher than the isentropic work, so it's the isentropic work over the actual work. So if you know the isentropic efficiency, you still follow the same methodology to solve for H2, but then you plug it into this equation to solve for your actual H2. And then using that, you can interpolate on the table and find an actual entropy as well. Okay, any questions on that? All right, so we're up to state 2, state 3. What do we know about state 3? Okay, it's superheated, right? Because we're going into a turbine. So that's going to be in table A6. But how do we fix the state?
Vapor.
Yeah, it's a superheated vapor, but we need another property value, right? How do we get it?
I assume you do something with that 96%.
Okay, so is that at state 3, the 96%?
Is this the
Is it,
That's
both?
the exit of both turbines.
Okay, it's at the exits of the turbines, right? So
4 and 6.
X is equal to 0.96 at state 4.
You could work backwards to get 3. You could solve for 4 using that, and then do 3 because that's isentropic.
That's right. So the isentropic assumption still helps us find state 3. Okay, so state 3, we know that S3 is going to be equal to S4. But instead of knowing this relationship and finding out what the enthalpy is at state 4, we work backwards. So H4 is going to be some value from table A5. So we find H4, we just look it up because we know the quality, right? So H is equal to H sub F plus X H F G at state 4. We do the same thing for state 6, H sub F plus X H F G. And this is at 5,000 kilopascals. And this one is at 12, oh no, that's not 5,000. Yeah, 1,220.
And then you use that 96% of X.
That's this, right. 1,220 kilopascals. Okay, so we're going to find H4 and H6 first, and then we go back and we know that the low pressure turbine, state 5 is at 1,200 kilopascals, and S5 is equal to S6, so we use that to find H6. No, H5. See, I'm backwards. Okay, so don't let something different throw you off. If you're used to being given the inlet conditions of the turbine, don't let it throw you off that you're now given the outlet conditions. Okay, you should be able to solve for both. All of these problems have enough specifications that everything is solvable. There's not like systems of unknowns that you have to use ease to solve. Okay, so now we know everything at every state, right? State 6, state 4, state 5, and state 3. So we find H3 because of this relationship, okay? So if we have all the enthalpies and all the entropies at every state, then we could solve for anything in our problem. The work output, the work input, the heat relationships, the thermal efficiency, the exergy destruction, we can solve for anything.
So the H3 you would interpolate based off the S3 equals S4?
So you find at this pressure where S3 is equal to S4, and that will give you your H3 in the tables. And if you have an interpolation function on your calculator and you haven't figured out how to use it yet, I would recommend that you figure out how to use it, because there's some interpolation on this exam. So if you do it by hand every time and you're quick and that's fine and you like that, but if you know how to use it, and make sure you know how to use it and you can tell when the answers are garbage because you plug things in wrong too, right? So don't always rely on it and just take whatever it gives you. Make sure that you have a good sense of a ballpark what the answer should be as well. So do a reality check.
So are we going to be given property tables?
Yeah. For now. You can't use your books. So you'll have property tables, but I'm not giving you equations. So,
This is still 2 pages, right?
2 pages. Okay, so the temperature at the inlet of each turbine, we can now do that because we know H3, we can find T3, because we know H4, no, H5, we can find T5. So part A is easy, we use this entropy or the enthalpy at the inlets to find the temperatures. Okay, so part A we'll figure out. Part B, the thermal efficiency, how do we do that? Okay, so work net out over Q in. So what terms do we have for work?
You'll have the work of the turbines.
Turbines, right?
And then you'll have the work of the pump.
Okay, work of the turbine 1, work of the turbine 2, work of the pump 1, work of the pump 2. So let's just write down these equations symbolically. What's the work of the turbine? 1.
H4 minus H3.
Okay, is it H4 minus H3 or H3 minus H4?
H3 minus 4.
It's out.
And how do you know?
Work out, so it's by bringing the negative through all the time.
Alright. So out
I just know it's 3.
is equal to in minus out. In is equal to out minus in. So if you're solving for a work out, then you're going to have to take the inlet minus the outlet. If you're solving for a work in, you're going to take the outlet minus the inlet. And if you do a steady flow, and if you can't remember that, if you're like, ugh, I don't remember which one is which, you can, that would be exactly how you would say it. You can look at your enthalpy values and see which one is bigger, but if you've done that wrong and you've looked up the wrong enthalpy values, that doesn't help you, right? So what is the other method that you could do?
Energy balance.
Do the whole energy balance in your turbine, right? Like, oh my gosh, I can't remember how this equation goes, so I start with Q in minus, minus Q out, plus work in minus work out is equal to work, H2 minus H1, whatever. Okay, so the work of the turbine 1 is going to be H3 minus H4. Work of the turbine 2 will be what? 5 minus H6. What about the work of the pump? Well, there's only one pump.
H2 minus H1.
It's H2 minus H1. So it's an in, which means it's out minus in. Okay, so that's our work term.
So do we not do anything with, like 2 and 3, how they go with the boiler or not?
2 and 3. Well, we haven't talked about Q yet.
Oh.
Okay, so Q, what Q terms do we have? Yeah, we have the boiler and the reheat, right? So we have Q coming into the system in 2 ways. And very important that if you have a problem like this, you recognize that there's 2 heat inputs there, right? When you're reheating something, you're adding heat again. So we have the Q in from the boiler, which is equal to what?
H2 minus H3.
Is it 2 minus 3 or 3 minus 2? Yeah. Q in is equal to out minus in, so 3 minus 2. And Q in from the reheat, what's that equal to?
5 minus 4.
H5 minus H4. Okay, so we solved this bad boy. We just need the actual property values, which we would go to the tables, and we'd be very careful when we're doing that during an exam to look up the right property values using the right tables. Yes?
You add the turbine and then subtract the pump, right?
Correct. So it's work of the turbine 1 plus work of the turbine 2 minus work of the pump for the work net out. And the Q in is Q in of the boiler plus Q in of the reheat process.
So this is a dumb observation, but you just take each individual part and make one megalodon equation.
Megalodon. That's the technical term for it. Yeah, so that's all you're doing. Which is why when you look at these massive systems, and it gives you a heart attack just to even look at it, you need to take a step back and just calm down and be like, okay, what is it? It's a bunch of turbines and heat exchangers and pumps, right? I know how to analyze those. So you do it one piece at a time, and you look at the individual components, and you'll be okay. It's when you try to look at the whole thing all at once, and you're like, where's it, and you get all freaked out, and you can't even do anything. Just take it one step at a time, and even if then you're struggling, and you're trying, and you're kind of confused, and write down your steps and what you're trying to do. Because if I understand that you were trying to do something and you just missed one little piece of it, I'm a lot more lenient than if you write down nothing, right? So partial credit is always good.
The thing, on a few examples, on the low pressure turbine section,
Yes.
We would have a thing where it'd be like y, then 1 minus y.
Uh-huh.
You only do that if it's clarified to do that?
Well, that's only when there's more than one outlet of a turbine. Like, this is an inlet. It's not an outlet, right?
You remember that was like when it had the other like heat exchanger thing?
So when there's
Oh,
a problem like this, you mean?
Yeah. Okay, that's when you have 2 outlets.
So you might see something like this on an exam and just like throw your paper down and walk out the door, right? Because you're like, oh, it's too hard, I can't do it. If you like Fs, that's acceptable to do that.
Everyone doesn't go through the curve.
Then everybody fails and I lose my job, and that's fine. So I'm Phoenix teaching next semester anyway, so it's okay. Thermo 2 doesn't happen next year.
I know, so
Next semester. Who knows what will happen in the future? I don't even know.
Yeah,
I just-
it's actually
You see all those getting A's?
What?
You see all those getting A's?
No.
But I mean, you can see if you want.
That one I do know and understand will never happen. Okay, so before we go to this example, let's just do something real quick. Where we draw the TS diagram. And we'll think about this. So I'm going to erase everything on this screen so I can draw this screen, the TS diagram on the same page. Because it's also informative to understand the TS diagram and where it comes from and be able to draw a TS diagram should it be asked of you. Just in case. So TS diagram, we always have this dome thingy. And then we're going to have lines of constant pressure. How many pressures do we have in this system? 3, right? So we have a pressure at 20 kilopascals. We have a pressure, and this is not to scale, at 1200 kilopascals, and a pressure at 5000 kilopascals. So 5000. Okay, so we know the condenser, state 1, is going to be a saturated liquid at 20 kilopascals, right? So automatically we can put state 1 on the chart. That's pretty easy. Actually, what I'm going to do, I'm going to draw this in red and the rest of it in black. Oh, actually, I need more green. I can do green. Ooh, look at that. Okay, state 1. All right, so what else do we know about some of these points? Like maybe states 4 and 6. What do we know about those?
Mixtures.
Okay, it's a saturated liquid vapor mixture at a certain pressure, right? And what is the quality? 0.96. So which side of the dome will that be closest to?
the right
The
side.
right side, right? So we could draw at 5,000 kilopascals. We're going to have a superheated vapor. But down here, we're going to have states 4 is at 1,200, right? And 6 is at 20 kilopascals. So we've got states 1, 4, and 6. We need to figure out where 2, 3, and 5 go. Where is state, from state 4, where is state 3?
Superheated.
It's superheated, and what do we know about the relationship between 4 and 3?
Same pressure.
Same, not same pressure.
Oh, no.
What is the same?
Same.
Entropy.
Entropy, right? This is a TS diagram, so a line of constant entropy is just a straight line up and down. So state 3 would be here. We could do the same thing on state 6 to state 5, right? So then it just remains for us to figure out state 2. Is that the only one left?
Yep.
Okay, what do we know about between state 1 and 2?
Constant entropy.
Constant entropy, and what pressure is state 2?
5,000.
Right, so we just draw up to there. So state 2 is here. So then we can draw our cycle, right, on the TS diagram with the arrows going in the appropriate direction. Not so bad. Pretty easy, right? Yes.
Would 4 not be on the curve?
It's not on the curve, it's just hard to draw it with these pens because they have a mind of their own. It's just slightly inside the line. 4 and 6, both. But I can't be very precise. Okay, any questions on this before we go to the next megalodon example? This one's the, like, if this one is megalodon, this is like less than megalodon.
Great white.
Whatever's the next tier below. The blue whalers. Ugh, okay. So we have steam regenerative Rankine cycle with an open feed water heater and a closed feed water heater. Right there and right there. Steam enters the turbine at 10 megapascals and 600 Celsius. Where's that? What state? 8, right? Okay, so this kind of like this green pen, 10 megapascals and 600 degrees Celsius. So state 8 is fully specified. We can find the enthalpy of state 8 very easily. And leaves the condenser at 10 kilopascals, right? 10 kilopascals is the pressure of the condenser. That means state 11 is 10 kilopascals and state 1 is 10 kilopascals. Steam is extracted from the turbine at 1.2 megapascals for the closed feed water heater. So which state is that? 9, right? This is the closed feed water heater. So it comes out at 1.2 megapascals. And at 0.6 megapascals for the open feed water heater. So state 10 is at 0.6 megapascals. The feed water heater is, the feed water is heated. Okay, so when it's talking about the feed water, it's talking about the stuff that's coming out of this pump. Is heated to the condensation temperature of the extracted steam in the closed feed water heater. What does that mean? So the feed water is heated. What's happening in this closed feed water heater?
Turn steam.
What did you just say? I heard two things at once and they combined and I'm hard of hearing. What? What did you say?
I'm not sure.
It's heating. It's heating. So from state 4 to 5, the temperature is increasing. All right? What temperature is it going to? That's the tricky part in this wording. Okay, so the feed water is heated to the condensation temperature of the extracted steam in the closed feed water heater. So the condensation temperature of the extracted steam. Where is the extracted steam?
9.
Okay, so from 9 to 6 is the steam that's coming through this closed feed water heater. So it is hot. It's giving up heat to the feed water. So what does that mean, the condensation temperature of the extracted steam?
Where it turns to steam.
Okay.
Like full steam.
Okay, so at what temperature does that happen? The saturation, not 100 degrees, that's only at atmospheric pressure. The saturation temperature. Okay, how do we know the saturation temperature?
Just look at the
Show
chart.
the pressure.
We know the pressure, right? We know the pressure of the steam coming through. We know it's condensing. It's going to condense at that pressure, which means the temperature is fixed, right? Okay, so coming out here is partially condensed steam. And if it's at a given pressure, this has to be the saturation temperature, Tsat, at 1.2 megapascals.
On superheated vapor, right?
So the saturated liquid vapor mixture.
Saturated.
Because a superheated vapor doesn't have a saturation temperature.
Right.
Only mixtures do. Okay, confusing, right? So back to this.
I'm sorry. What is the for table A6? What is the temperature beside the pressure?
That's the saturation temperature.
And you just said there's no saturation temperature.
Oh, table A. Oh, that's table A6 is superheated.
Yeah.
So the temperature is just the temperature and the pressure. So it's it's columns and pressures. So there's a temperature. Are you talking about the temperature at the very top of the column?
Yeah.
Yeah. So that's the saturation temperature, meaning that values at or below that temperature don't make sense in the superheated table.
Okay.
So the superheated vapor does not have a saturation temperature.
Right.
Because once it reaches that temperature, it's now a saturated vapor.
Okay.
So it gives you the temperature on the table just to tell you that that's the bottom limit for where that table can go.
Oh, okay.
Yeah, so it's just there and it's not telling you that superheated vapor has a saturation temperature. It's just saying like this is any value below this number doesn't make sense because it's a saturated vapor, not a superheated vapor.
Okay.
Okay, back to this. So the feed water is heated to the condensation temperature of the extracted steam. What that means is that T5 is equal to T6. And T6 is going to be the saturation temperature at 1.2 megapascals. Okay, do you guys see that? Or you just taking it as fact because I said it?
So
You seem trustworthy.
you just assume it
I'm
because
almost
it's in the same box, or?
No, because the problem told us that the feed water coming into this closed feed water heater, which is coming out of the pump, state 4, is heated to a certain temperature.
So the way it's flowing, is it flowing from 4 to 5 and then 9?
No, it's
Six?
flowing from 4 to 6.
Oh,
And from, sorry, 9 to 6, 9 to 6, and from 4 to 5, yes. So this is a separate line.
and the coil there in the middle, that's the,
It's a heat exchanger. Because in a closed feed water heater, the main difference between closed and open is the fluids don't mix. It just exchanges heat. Whereas in an open feed water heater, we have a mixing chamber where the fluids all come in and mix together.
And it's using 9 to 6 to heat 4 to 5.
Right. Yeah. So heat is being lost from 9, it's condensing at the saturation temperature, and it's giving that heat to 5. So T5 it's heated up until it reaches that saturation temperature. T5 is equal to T6. Okay. So at state 5, we know the pressure is going to be the same as the boiler pressure, which is what? 10 megapascals. And that T5 is equal to T6. So that state is fully specified. Let's look at some of the others. Okay. The extracted steam leaves the closed feed water heater as a saturated liquid. Okay, so what state is that? This is state 6, right? So at state 6, X is equal to what? Is it 1 or 0?
1 is the vapor, 0 is the liquid.
Yeah, X is equal to 0, and the pressure is equal to 1.2 megapascals. So this one is fully specified. Okay, so state 5 is good, state 6 is good, state 8 is good. State 7, this is a throttling device. What does a throttling device do?
Drop the pressure.
Throttles, so it lowers the pressure and does what? Constant enthalpy process. Okay, so H7 is equal to H6. That one's specified for us. All right, so we have 5, 6, 7, and 8. What about 1, 2, 3, 4, 10, and 11? Oh my gosh. How do we even do this? Okay, oh, here's some more info. You may also assume the fluid leaves the open feed water heater as a saturated liquid. What state is that? Okay, so X is equal to 0 at state 3, and what is the pressure at state 3?
0.6 megapascal.
0.6 megapascals. Okay, so state 3 is fully specified. What about state 1? X is equal to 0 there. That one is fully specified. State 2, how do we find state 2?
0.6 megapascals.
Okay, the pressure is 0.6 megapascals. How do we find the enthalpy, or how do we find?
Forward pump thing.
Okay, so we do the work of the pump, right? So H2 is going to be equal to H1 plus V1 times P2 minus P1. So now state 2, we know the enthalpy, which leaves us with states 9, 10, and 11. How do we find the enthalpies at 9, 10, and 11?
You find the enthalpy.
Enthalpy. How do we find the enthalpy? How do we find the entropy? What's the entropy at 9, 10, 11?
Well, you get it at 8, and 8 equals 1.
Yeah. So S9 is equal to S8. S10 is equal to S8. S11 is equal to S8. So we know a pressure and an entropy at each of those states. Now they are all fully specified. So we're left with, I guess, actually state 4, we haven't done yet. But we would follow the same procedure. H4 is equal to H3 plus V3 times P4 minus P3. So we know all the enthalpies at all the states. It just took a little bit of work to read and understand the problem to know about this extracted steam, condensation temperature, and all of that information. And these examples are done and they're scanned online if you don't want to. Okay.
Do we know the pressure at 4?
The pressure at 4. What is the pressure at 4 going to be?
1.2.
Should be the same as coming out.
0.2.
Should we
What
say
is the
it's
pressure
going
at
in?
4?
0.6.
I hear a couple of different answers. How do we know?
Pressure doesn't change inside, so that's me saying going in.
Yeah, so whatever's going into the boiler should be the same as pressure state 4, right? So state 5, state 4, state 8 are all at 10 megapascals. Okay, so how do we find the mass flow rate through the boiler for a net power output of 400 megawatts? So work net out is going to be equal to the work of the turbine minus work of pump 1 and work of pump 2. And that's equal to, if we do it in the rate form, 400 megawatts. We have to figure out what will that mass flow rate be that will allow us to have a network output of 400 megawatts. Well, let's look at our turbine and what terms we need. So the work of the turbine is going to be equal to H8 minus Y times H9 minus Z times H10 minus 1 minus Y minus Z times H11. So what I've done is I said the work of the turbine is equal to what's coming into the turbine, state 8, minus what's coming out, states 9, 10, and 11. And these all have associated mass flow rate ratios or fractions with them. Okay, so in order to find the work of the turbine, I need to know Y and Z, which I don't currently know. So I have to do a couple of energy balances. So I do one on the closed feed water heater, an energy balance, and I know that Q out is equal to H9 minus H6 times Y. Okay, so the Q out of the steam coming from the turbine is going to be equal to the Q in of the steam or the feed water that's coming from the pump back to the boiler. So it's H5 minus H4. And is there any mass fraction multiplied by that? What is that mass flow rate from 4 to 5? Okay, there's 1 minus Y minus Z. That's the mass flow rate that's coming in at 2. But when 2 goes into that open feed water heater, and it's combined with 10 and 7, then we have 1 minus Y, right? Because we have a Z added to it. And then after it comes out of the feed water heater, the closed feed water heater, then we have 1 minus Y minus Z, right? So
Is that H5 or H4?
So from 4 to 5, we have all of the flow coming back through. Can you see that? Because in the open feed water heater, we've added the Y and the Z back in. Okay, so we don't need to multiply this H5 minus H4 times anything. So if we do Q out is equal to Q in, then we find Y is equal to this ratio H5 minus H4 over H9 minus H6. Okay, so we solve for Y. To solve for Z, we need to do an energy balance on the open feed water heater. So we find that Z times H10 plus y times H7 plus 1 minus y minus z times H2 minus H3 is equal to 0. So we can rearrange and solve for z. So if you look at the open feed water heater, you look at all those energy terms coming in. It's coming in at 10, 7, and 2. 10, 7, and 2. And it's leaving at 3. So in minus out is equal to 0 because it's a steady flow system. We solve for z is equal to H3 minus H2 minus y times H7 minus H2 divided by H10 minus H2. So now we know z. So we can plug that back into there to find the work of the turbine. Similarly, the work of pump 1 is equal to 1 minus y minus z times H2 minus H1. That's that first pump. And the work of pump 2 is equal to H4 minus H3. So work net is going to be equal to the work of the turbine minus the work of pump 1 minus the work of pump 2. And to solve for the mass flow rate, it's going to be this W dot over our work net, which is the 400 megawatts divided by a bunch of stuff. And in my scanned solution, I somehow have plus signs here. That's not correct. It should be minus signs. Okay, so then for part B, the thermal efficiency of the cycle. What is the thermal efficiency of the cycle? What's the equation for it? Is equal to work net over Q in. So we already solved for this work net. Q in is equal to what? Where do we have a Q in?
Just the closed feed water heater and boiler.
Yep. So we have an H8 minus H5, which is the Q from the boiler. And then the Q from the closed feed water heater is no, that's not a Q in because that's a regenerator. So we don't have to worry about that one. So Q in is just the Q in from the outside, which is the boiler. If you were to draw a system boundary around this entire thing, that's the only Q you would see. Okay.
So you have when you're doing the work net out, you have to find the turbine and then the two pump works. But then first you have to find the Y and the Z.
Right.
Based off the closed and open feed water heater.
Yeah. So that's the trick, right, in some of these problems is that sometimes you'll go to solve for the turbine work and you'll realize, oh, I don't have yet these other terms, right? I don't have a certain enthalpy, or I don't have a Y or a Z or whatever it is. So then you go back to your problem and figure out, how do I solve for those things? How do I find another equation? So it may come in the terms of doing an energy balance on a heat exchanger or a feed water heater or a mixing chamber, or we're looking at your throttling device again. You just have to see what you have and what other pieces of the puzzle you haven't analyzed yet. So anytime there's a heat exchanger or a mixing chamber or anything else where multiple fluids are coming together, maybe the turbine, then you can do another energy balance or a mass balance or sometimes both to figure out what pieces you don't know.
What'd you do in the part where you had the Q for the closed feed water heater? Is that Q out minus or equals Q in?
Right, because it's two distinct fluids, right? So there's one coming through from the turbine, and then there's another coming through from the feed water back to the boiler. They're not mixing. So there's heat coming out of this, Q out, that's going into here, Q in. So heat from that steam is being transferred into the other fluid. So what you're saying is Q out is equal to Q in. So it's just.
So like the Q out of one is the Q in of the other. Okay.
Any other questions on this example? Okay, are you gaining confidence that you can solve anything? What is this? Yes.
Alright. The T saturation at the state 6,
Yes.
do you have the value?
No, I didn't do any values in the problems, I just did all.
Is the value in that's the same as in the pressure table? So I'm just curious.
What do you mean?
The temperature you get is the same one that we were talking about earlier.
Oh yeah, it will be. Yeah, because it's telling you what the saturation pressure is at 1.2 megapascals.
Right.
Yeah.
And that's the what we use for that value.
For
For
T5.
T-sat.
Yeah, T6 and
Six.
T5 are the same temperature. And that's the value you use. Yeah, so the temperatures that are in table A6 for the superheated region are just telling you what the saturation temperature is for that pressure. So if you get to that temperature, you're no longer superheated vapor.
Right.
So it should match. The tables
Okay.
should match. And if it doesn't match, it's an error. Yes.
Is the TS diagram for number 2 in the notes?
It is, but let's do it. Let's do it. Okay, let's go to the other screen because it's easier to do it. And you can see, oh my god, see nothing. Okay. Let's draw this TS diagram. Maybe I'll do this. Just temporary. Okay. So TS diagram for this problem. How many pressures do we have? 4 pressures. I better make a big jump. So 1, 2, 3, 4. Again, not to scale. So we have 10 kilopascals, 0.6 megapascals, 1.2 megapascals, and 10 megapascals. Okay, so some points we know easily, right? Like coming out of state 1 is a saturated liquid at 10 kilopascals. What's another one that we know is a saturated liquid coming out of state 3 and state 6? Okay, so what's the pressure at state 3? Okay, 0.6, state 3. What's the pressure at state 6? Yeah, it's 1.2. So there's 1, 3, and 6. What happens between 6 and 7? Okay, it's throttling to a lower pressure, so it's going from 1.2 back down to what? 0.6. And a constant enthalpy process just always kind of looks like a curve in. We could find the exact point by finding x, but we don't need to necessarily know the exact. Oh boy, what have I done? What have I done? Okay. So this is state 7. So 7 goes to 3, right? Here 7 goes and it mixes with 3, but 7 also combines with 10. And what is the state at 9, 10, and 11? Coming out of the turbine, it's either going to be a superheated vapor, saturated vapor, or a saturated liquid vapor mixture. If we look at the problem, we realize that at state 9, it's still superheated, but at state 10 and state 11, it's a saturated liquid vapor mixture. But from 8, 9, 10, and 11 is a constant enthalpy, or no, constant entropy process. So 11, 10, 9, and 8 are all going to be on that same line. And if we're drawing lines of constant pressure, this one is there, that one there, there. Okay, so 8, 9, 10, 11 are all on a straight line. That leaves us to figure out 4, 5, and 6, and 2. Okay, so what happens between state 1 and 2? Okay, it's isentropic, so that's going to be straight up and down. State 2 is right there. It's a compressed liquid just outside the dome. What happens between state 3 and 4?
Pressure.
Okay, pressure increases. It's isentropic, but what pressure do we go to between 3 and 4?
0.6 to 1.2.
Yeah, we go from 0.6, not to 1.2. We go all the way up to 10.
Oh, that's right.
So it's an isentropic process from state 3 to state 4, all the way up. And then between 4 and 5, and this actually doesn't work out. Hold on, I gotta redraw this line to be steeper. Because from state 6 to state 5, you can imagine this is a straight line, is a constant temperature process. So T5 equals T6. So sometimes you have to adjust. 1, 2, 3, 4. This is state 5, and this is state 6. So we'll assume that it's actually up like that. Okay. So we go 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6. But from 5 we also go to 8, like that. So, and then some of the flow from 7 is combined with flow from 10. And some of the flow from 9 is combined with flow from 6. So that goes that direction. And this goes this direction. This goes this direction.
So if we have to draw that in the test, you're gonna be pretty lenient on that.
I'm mostly concerned that you understand how TS diagrams work. Okay, moving on. Maybe. My keyboard's not working now. Awesome. Alright, so now we're to this example. I'm going to try to make this a little bit quicker. This one's an easier problem anyway. So looking at this, what type of a device is it? Before you even start solving it, making that recognition that it is
Stage.
a what?
Refrigerator pressure.
A refrigerator. How's a refrigerator different?
QLs.
Okay, the QLs are going to be different, opposite of what a heat engine would be. And you have a work input, a net work input. Okay, so two-stage compression refrigeration system with an adiabatic liquid vapor separation unit. Okay, liquid vapor separation unit, we haven't ever talked about those. But guess what? It's easy to deal with because you understand thermodynamics. With R134A as the working fluid, the system operates the evaporator at negative 32 Celsius. Where's the evaporator? It's at the bottom, so this is negative, I'm going to do it blue, negative 32 degrees Celsius. The condenser is at 1400 kilopascals. Where's the condenser? The top, 1400 kilopascals. And the separator at 8.9 degrees Celsius. What's the separator? It's that thing in the middle, 8.9 degrees Celsius, that we have no idea what it is. But do you think you could guess what it does?
Probably separates the hot and cold.
Separates not,
The fluid.
yes, hot from cold,
Vapor and liquid.
vapor and liquid. Okay. So if we look at this separator, we have to pay special attention to what direction things are flowing in and out of it. And then we can make pretty good assumptions on what exactly is going on. Okay, so if it's separating fluid, what do you think is coming out at state 5?
Saturated liquid.
A saturated liquid, so X is equal to 0. What's coming out at state 1? Steam, so X is equal to 1. All right, the refrigerant is circulated through the condenser at a rate of 2 kilograms per second. So which mass flow rate is the condenser flow rate? The top one, right? E equals 2 kilograms per second. This was also another issue I saw in the homework, is using the wrong mass flow rate. That you assigned it to the wrong part of the problem. So be careful about things like
You
that.
said 1 is a vapor. Does the color not matter? I mean, should we not look at the color?
Yeah, because blue
Yeah, don't
usually
look at
means
the
liquid.
colors, because it should be red.
Okay.
I'll just recolor it here.
Yeah.
All right. Okay. Determine the rate of cooling and the power requirements. You may assume the compressors are isentropic. Yes. And that the refrigerant is a saturated liquid at the inlet of each expansion valve. Okay, so we already determined it was going to be X equals 0 here, but where's the other expansion valve inlet? State 3, X is equal to 0. And a saturated vapor at the inlet of each compressor. So we already know it's a saturated vapor here at state 1. Where's the other saturated vapor? 7. X is equal to 1. Okay, so let's just go through our states and see if we have enough information to solve these problems. So state 1, X is equal to 1. Right? What else do we know about that state? Yeah, it's 8.9 Celsius, so we know the temperature is 8.9. We know everything about state 1. State 2, what do we know?
S2 equals S1.
Okay, S2 is equal to S1. What else?
Mass flow rate.
We know the mass flow rate. Does that help us find the property? We have a pressure, 1400 kilopascals, so P is equal to 1400 kilopascals. Okay, what do we know about state 3?
Pressure.
We know the pressure is 1400 kilopascals still. There's 1 there. And X equals 0, so state 3 is specified. State 4, what do we know about state 4?
Nothing.
We do know something.
The,
It's isentropic.
It's isenthalpic, right? So H4 is going to be equal to H3. There's one other thing we know.
temperature?
We know the temperature is equal to what?
8.9.
8.9 degrees Celsius, because the separator is operating at a constant temperature. So state 1, 8, 5, and 4 all have to be 8.9 Celsius. Which tells me that on state 5, also, T is equal to 8.9 degrees Celsius, so we know everything about that. We can figure out the enthalpy. State 6. H6 is equal to H5. State 7. Yeah. 32. Negative 32 degrees Celsius. And state 8. Okay, so it's 8.9 degrees Celsius, and what else?
S8 equals S7.
S8 is equal to S7. Every state is fully specified.
Can you say that the temperature at 6 is negative 32 degrees Celsius or only at 7?
You can only say that it's 7. Probably best to just say it at 7. It's likely to be a constant temperature process. So probably 6 and 7 in this problem are the same temperature. Yeah, but this isn't necessarily going to be a saturated liquid vapor mixture. If it ends up in the compressed liquid region, then it might be a lower temperature than what's coming out of the evaporator. In this problem, it's the same. It ends up being the same, but You can't necessarily assume that, you'd have to look at the enthalpy and check. So using, where you'd have to be given a pressure information to be able to find that, but it's not necessarily the same. Okay, so we need to find the rate of cooling. What is the rate of cooling for a refrigerator? What side of it are we looking at? Yeah, this is the one everybody had trouble with, for the heat pump.
Is it QL or work, or, wait, what is that?
QL is the rate of cooling. Q dot L, right? Q dot L. Should I do that one in blue? Q dot L is equal to M dot times QL. Where's QL?
It's the lower part.
It's the lower part, the evaporator side. Okay, so this is going to be your QL. This is going to be your QH. So what the evaporator is it is absorbing heat from whatever you're trying to cool so that you can have a lower temperature in that area. Right? So make sure you understand it's opposite from the heat engine, that your Q sub L is going to be down there. Okay.
Well, is M6 going to equal M2?
M6 does not equal M2, so how do we find M.6? Energy balance on the evaporator. Okay, so M.6 times H, be out minus N. So Q in is out minus N. 7 minus H6 is equal to QL. Does that help me find M6? Q dot L. Can I find M6 from that?
Separator.
You have to do an energy balance on the separator. That's where mass flow rate 2, which is given, intermingles with mass flow rate 6. So we do the energy balance on the separator. We have M.6 times H 8 plus M.2 times H4. So that's what's coming into the separator, H8 and H4. It's M.2 minus M.2 times H1 minus M.6 times H5 is equal to 0. So then we solve M.6 is equal to M.2 times H1 minus H4 over H8 minus H5. So now we know M.6, we can plug it into this equation to find Q dot L, that's part A. For part B, the power requirements for the system, so we need to find out how much power goes into each compressor. So W dot N is going to be equal to the work of compressor 1 plus the work of compressor 2, actually the power of 1 and power of 2. So it's M.6 times H8 minus H7 plus M.2 times H2 minus H1.
Can you repeat what you said about the whole rate of cooling for the refrigerator to the heat pump?
Yes.
QL is the rate of cooling for a refrigerator, but for a heat pump, the rate of cooling is QH.
You're not cooling with the heat pump, you're heating.
And is it flip?
No,
Wait,
the system is exactly the same. You're just looking at the other side of it instead of here. So be very careful when you read what it's, and think about it for a minute. Okay, a refrigerator does what? Removes heat from a cold space to make it colder. And that heat is absorbed in this evaporator, whereas with a condenser, heat is being removed from the fluid to go somewhere else. Okay, now we have 4 minutes to talk about the rest of these. Okay, the TS diagram for this is on the examples. You can look at that on your own, make sure you understand it. These ones we don't have a lot to go through. I just want to talk to you about these Maxwell relations And understanding, first of all, that you should have this written down on your note sheet somewhere, all of these equations. And then understanding that these are equivalent relations. That's the main deal with the Maxwell relations, is we want to know, okay, if we're told to find this, that we actually can use that equation to find it. Or if we're told to find this, we can use that equation to find it. So there's an example that you can do on your own. The solution's also on the thing. Make sure that you can do this example, you understand how it works. And then the other things that I want you to focus on and know how to do is being able to find properties. Okay, so a change in enthalpy using this equation, maybe, but not necessarily. But understanding and knowing how to use the departure charts. That part is a key component to what you should be able to do for the exam. So if you have the ideal gas equation to solve for enthalpies, or if you look them up in the tables, how do you use the departure charts to find that correction factor for any of these? So internal energy, enthalpy, so these are all good equations also to write down on your sheet, and entropy. And then the Joule-Thomson coefficient. So we did some examples in class previously where we looked at points above and below a certain value. So at 500 kilopascals and 300 degrees Celsius, we looked at like 600 kilopascals and 400 kilopascals. And we find the slope of that line. So for given a constant enthalpy line, so we find H at this value, and then we go to like 300, you go like 400 kilopascals and 600 kilopascals, where H is equal to this H1, H is equal to H1, and we find a temperature, right? Do you remember doing that? So then you plug that into the equation that it's approximately equal to a delta T over a delta P, using this 400, 600, and whatever you look up your temperatures. Okay, so that's a way to approximate how this Joule-Thomson coefficient will look, whether it's a positive or a negative slope, and then you can use that to find an unknown temperature. So if we know the slope at this point at 500 kilopascals and 300 Celsius, then we say, okay, then what is the temperature going to be at 800 kilopascals? So we use that estimated slope to find an estimated value at a new pressure. Does that make sense? To review that, make sure that you know how to do that. And then the difference between gravimetric and Molar analysis. We're not going to worry about the Amelgat's and Dalton's law so much on this exam, but you should be able to take either molar form or mass form and manipulate things to find like an average mass, an average gas constant, an average molar mass for any combination of things. And then once you have that, how would you find a volume? How would you find a temperature or pressure, things like that. Okay, so the focus concepts, this slide actually isn't in, so if you want to take pictures, because I added it. These are things I want you to really kind of make sure that you understand the concepts of, right? So what is the Rankine cycle? What does it consist of? What does it do? You know, what are the 4 steps of the basic ideal Rankine cycle? And then when you add these modifications, how does it change your cycle? So if you add cogeneration or regeneration or reheat, what does that do to the base Rankine cycle? And then, of course, being able to approach any megalodon and solve it. That's fun, right? Chapter 11 is all about refrigeration and heat pumps, making sure you understand the difference between a refrigerator and a heat pump, depending on what you're asked to solve. And then if you were to look at some of those bigger refrigeration systems, the megalodon refrigerators, how would you solve those problems, right? And then from chapter 12, I'm not going to ask you to like prove any of the Maxwell relations, but you should know how to use them. And you should know how to calculate properties for ideal gases using some of those equations that were given previously. And then using the generalized charts, there is a problem using those generalized charts, so make sure that you know how to do it. Yes.
You said last week there was a big one megalodon problem, and then a few like smaller
Yes.
ones, and then in addition to some of these little tidbits of.
Yeah, so there's conceptual questions, like I always do true or false, or definitions, or there's some of those problems. Then there's some easy, you know, like on the last exam, how you had just like a heat engine and you have to figure out like thermal efficiency or whatever. There's some easy problems that are like 10-point level problems, and then there's a big problem at the end. So manage your time wisely. Don't get stuck spending all of your time on a 10-point problem. Look at the point values and figure out where you can spend your time. If it's going to take you all class period to do Megalodon, that's, you know, a third of the test, whereas maybe you could spend the whole class period doing the other 2/3 of the test and get a better grade, right? So you got to figure out where to do that. So study work, focus more on the concepts of how to solve these problems than trying to memorize, okay, well, if it's this type of system with a reheat and a regenerator, then the equations are, you know, you can develop those equations for any system. You know how to do it. You should know how to do it. So concepts are more important than memorizing setups. Okay? All right, good luck. See you on Thursday.
Quick question, do we ever, like chapter 13, would we ever have to mix the gas stuff and mold stuff in like a ranking thing? Or no?
Not on the exam. That is, stuff like that is coming in a future chapter.
At least it's on the ranking.
No, it's not on the exam. Not this.
Save that until last.